Alright everyone, as promised, I'm going to be finishing up the infinite square well problem by normalizing the wave function. The normalization property is also regarded as the statistical version of quantum mechanics invoked by none other than Max Born himself. So this is also regarded as Born's rule, if you will. So the normalization property says that if we take the integral across all space from negative infinity to infinity, and our integrand being the conjugate pair of the wave function, where we have psi conjugated and psi not conjugated times, or as with respect to position here. So dx is going to be our integration constant. Okay? So we have our two distinctions that we have to be a little bit explicit about, because if we have a capital psi, that is a function of position and time, not just position. So that is important to note here. When we're talking about, say, psi, the lowercase psi, that's generally described as being the function of position, whereas the uppercase right here is just a function of position and time. Now, the decomposed version, at least some physicists, particularly in Griffith's quantum mechanics, they tend to describe the time-dependent part of the wave function as the wiggle factor. So just a interesting little tidbit, but from now on we will be regarding the time-dependent version of the wave function as the wiggle factor. So that is what we're going to be describing, and hopefully at this point you'll know what I'm talking about now. So let's move on. So we have our integrand. Now, what are these? We derived the position-dependent part of the wave function last time. So let's write that out here. So if we have our time, or our time and position dependent, our spatial dependence, x and t of the wave function, that is going to be equal to our position dependent part of the wave function, or and then our eigenfunction e raised to the negative I times e over h bar right there. Okay, so this is our full description. However, the position dependent part of the wave function is going to be equal to our normalization constant a, we'll call it, multiplied by sine of pi n times x over L. And then we have our wiggle factor, which is e raised to the negative I e t over h bar. All right, so this is what we're going to be relying upon here for our normalization. Now, it is important to note that the normalization is, this particular description has to be equal to 1 if we are going to be describing quantum mechanics in terms of statistical likelihood of a particle being in any given position. Now, if we're integrating all over space, then there's 100% chance that you will find the particle somewhere, okay? So this is going to be equal to 1, okay? For those who have experience in quantum mechanics, I'm sure you were just pulling your hair out wondering why I didn't set it equal to 1. Well, there we go. So now we have Born's rule, our normalization factor here, and we're going to be using this, except we're not going to be integrating all over space, because before, when we set up our boundary conditions, that is going to be instead what our limits of integration are in fact going to be. So it's going to be from 0 to L is what we had imposed for our boundary conditions in our last video. So let's start writing this out now. So we will have our integral from 0 to L with our wave function conjugated, and that with respect to dx equals 1. Okay, So let's start plugging in our wave function conjugate pair here. So we're going to have now our integral from 0 to L, and our wave function conjugated is going to be the positive version for our complex component here. So we're going to have a times sine of pi n x over L, and then our wiggle factor, which is our non-negative component, which is going to be I times E divided by T over H bar. Okay, and that is going to be multiplied by our non-conjugated pair. So we're going to have a times sine of pi n x over L. And then our wiggle factor, of course. So negative I E T over H bar with respect to x. Now this looks like a lot, but it's really not bad. And the perceptive amongst you probably already see how this can be simplified. So this right here, these two will just cancel out to 1. Okay? So let's now sort of multiply all this together and bring our constant outside of the integral. Okay? So we're going to have an a squared from 0 to L, where we have sine squared of our argument pi n x over L with respect to x. Okay, so now we can just invoke a trig identity, which over here we'll have as sine squared of theta is equal to 1/2 1 minus cosine of 2 theta. Okay? And that will radically simplify this. So we're going to have now a squared outside here. So a squared, where we have our integral from 0 to L. And now we have 1 over 2, 1 minus cosine of 2nx over L. So 2nx over L. And that is with respect to x. Okay, so let's use the property of linearity and distribute this integral sign across. And we're going to have a squared. And we can also factor out that 1/2. So we're going to have a squared over 2, where we now have our integral from 0 to L of 1 dx minus our integral from 0 to L of cosine of 2n pi x over L. And that is going to be with respect to x. Okay, great. So now we can solve this fairly simply. So we have our antiderivative of 1 with respect to x just becomes x. L minus 0 is just L. So we're going to have now our a squared over 2. So a bracket there. We have L minus, okay, so we could probably just do this in one step. Sorry for those who want to see every little sort of substitution that I make, but I mean, it's not too difficult of an integral to solve. So from 0 to L, we have our cosine 2n pi x over L. Well, the integral of cosine is just sine, but we have to take the argument, so it's like a reverse chain rule, and then flip the numerator and the denominator, okay? So we're going to have, let's write this here. Maybe rewrite that. So from 0 to L, we're going to have L over 2n pi, then multiplied by sine of 2n pi x over L. Okay, so now we can start taking our limits from L to 0 here, and this brings up an interesting point that we need to make. So there's no x factor here, so we're not making any substitutions there. But from L to 0, if we substitute L here into the sine function, we have sine of 2n pi, because the L's just cancel there, okay? So what is sine of 2n pi? Well, we set up our conditions for what n must necessarily be in the previous video. And we set them in such a way that sort of preserve the physical, basically the physicality of the entire situation. Because if we were to choose, say, n equals 0, then the wave function would vanish, and that would be a violation of physical properties and conservation laws. So we don't want to do that. So our conditions are n equals 1, 2, 3, dot, 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 and just kind of goes on forever. So any integer multiple of sine of 2n pi is going to be 2 pi, 3 pi, 4 pi, and so on. And sine of any of those values is always going to be 0. Okay? So this right here just cancels out to 0. Okay? Now, we have everything we need. So if we take your stuff, bring your eyes over to this part of the board, we have a squared L over 2 is equal to 1. Remember that I wasn't writing it out here, but this is the condition that has to be upheld here. So a squared L over 2 equals 1. Now we can solve for a. So a squared is equal to 2L over L. And then we can take that, and we have a is equal to the square root of 2 over L. And there we have it. That is our normalization constant, which is perfect. So we can actually now fully write out our entire wave function. Okay? So we have our wave function, and that is a function of x and t, which is equal to the square root of 2 over L sine of 2n pi, or sorry, not 2n, it's just n pi x, n pi x over L, and that is also inclusive of our wiggle factor. So e to the negative I times our energy multiplied by time over h bar. And there we have it. That is our entire wave function along with our normalization constant. So not too bad, fairly simple integral to solve. And I'm going to bring this on over to the computer where you can see a little bit of Python code to see the discrete energy levels visually on a Python plot.
Alright, so here we are. As before, I am still using this headset because my audio with my camera mic is just really bad. And I know this isn't perfect either, but I hope you'll forgive me. But so here we are in my Jupyter notebook, and we are going to represent the wave function. Okay, but we're going to represent it just in terms of its position. Not gonna include our wiggle factor in this case, just so you can get a simplified sort of illustration of how this looks. And it'll look vaguely similar to what I showed you in the beginning of my last video about the infinite square well with the mana presentation. I'm just going to kind of show you a static representation here. Okay? So first we just need to set up our length for our box. And it can be really anything we want. We'll just pick 10 here. But it can be anything you want so long as you include your array of x values from 0 to whatever L is, okay? And we'll actually do that right now. So x is equal to np dot arrange from 0 to L, and then we'll go in steps of 0.01 here, okay? Alright, so now we can actually, let's write out our n values. So our n values that we're going to be iterating over, or rather what we're going to be evaluating for each subsequent wave function, we're going to have some n value from 1 to whatever we choose. But we're going to create a little list here, okay? So our list is going to go from 0, 1, oh, not 0, 0 would not be correct. So 1, 2, 3, 4, we'll go to 5 here, okay? We'll stick with that, alright? So now what we can do is define our wave function. Let's create a function for that, okay? So define it's just going to take one input value of n for this particular function. So let's create an argument that is going to be what we're putting into our sine function. So our argument is going to be, we have n times mp dot pi, pi times x, and that is going to be over L, right? So that was our argument for our position-dependent wave function, okay? Now we're going to actually put that into our wave function, where we now have, I forgot a crucial component here. We need our normalization constant, of course. So our normalization constant is going to be equal to the square root of 2 over L, right? Over L. Great. So that is our normalization constant. So our wave function, of course, is norm times our np dot sine of our argument. And there we go. Now we're just going to return our wave function. And there we go. So that is going to be our function. Now we need to basically create a for loop and iterate through each subsequent n value and evaluate it for those points. Okay. So we're going to have we'll do for I, or we'll do ni, because we're indexing our n values here. So for ni in some range, right, from 1 to the length of 1 to the length of our n values. And we're going to be plotting each and every one. Okay, so plt dot plot, where we have our x values for our horizontal axis, and then our wave function, and we're going to be putting every indexed n value there. Okay, so now what we can do is we're going to create a legend to represent each n interval here. Okay, so n sub 1, n sub 2, n sub 3, right? So we'll put label equals, let's see here, we're gonna do a little bit of LaTeX here. So we're gonna put our quotes here, and we're gonna have our dollar signs, and we're gonna have n sub percent g, and that we're going to be putting every subsequent n value in for. Okay, so we're gonna have percent, no comma there, percent n. Okay, percent n I believe that might be wrong, so sorry to make it the wrong legend here, but we'll fix it if it's wrong. So plt dot legend, and that will give us what we need. Now, this should work, hopefully, assuming there's no errors, but what we're going to want is, let's just create, let's do our due diligence and label our axis axes, and then create a title. So plt dot title, we'll just do infinite square well. Just call it that. Okay, and then we will create our y-axis, plt dot y label, where we have, say we'll call it psi, okay, because that's what we're doing. So we can actually use some fancy LaTeX format, psi. Alright, so that should be our y, and then plt dot x label, and we'll just do n, okay? We'll just keep it in LaTeX format. Okay, so we have our n, so every integer multiple there, and let's see what this looks like. Oh, I should do plt.show so I get rid of that. Show. And it looks good. So yeah, we have all of our variable values evaluated at our specific n components, and our legend seems to work very well. So we have n sub 1 being our ground state with 0 nodes, and then n sub 2 our orange, where we have our singular node here, where it is going from 0 to 10. And we can actually make this look a little bit nicer by just adding some horizontal and vertical lines along the 0 part of the axis. So we'll do plt dot ax each line, where we have 0, and we'll do 0 to, well, not just 0, excuse me. So 0, and then we'll have a color, call that black. So black is K, don't ask me why it's K, that's just what it is. So color is K, and then we'll have line width, because that's going to be a little bit disorienting if we just leave it this way. So line width equals 1. Now we'll want a vertical line too. Give us that. So 0, so ax v line, vertical line. We'll do that. Sweet. And actually, let's just change the font size of our wave function. Okay. So font size is equal to 21. And then similarly, we'll do that with our x-axis here. Okay. Sweet. So they're all consistent. Well, there we go. So now that looks great. Now we have our infinite square well problem, and this has been illustrated and solved for ad nauseum, I presume. But there we go. I hope you guys really enjoyed this. I enjoyed making it. I'm sorry it took me a while, but I'm doing a lot more quantum mechanics these days, so presumably in the future I will be doing some more videos with quantum mechanics, and we will also go into some more specific details about why the normalization function works, and specifically how it remains unchanged through arbitrary increments in time. And we're going to be going through all of those little details, and I mean, just to sort of like, develop some affirmations and establishments within the context of quantum mechanics, because it's very important that your wave function, or the wave function that you're solving for, remains normalized through all points in time, and that can be proved relatively simply. It's just a simple integral where you just take some time-dependent integral or time-dependent derivative, bring that inside the integral, and just use the Schrodinger equation by inputting your necessary conjugate values, and so on and so forth. So we'll probably be doing something similar to that. We'll go into maybe some Braun-Ket notation later on, and we may even very well solve for the quantum harmonic oscillator or the finite potential well. So stay tuned, and thank you for watching.